Hello, and welcome to the AWS Certified Machine Learning Specialty course. My name is Elliot, and I'll be your guide throughout this journey. I'm excited to help you prepare for the AWS Certified Machine Learning exam. And today, we'll start with an introduction to the course, what it covers, who it's for, and how it can help you achieve your goals efficiently. Before we dive in, let me share a bit about myself. I'm a staff data scientist at a publicly traded e-commerce company in the States, where I work with massive data sets and leverage AWS services like SageMaker and Redshift. I'm also a Kaggle Grandmaster and have written several best-selling books on AI and data science. Additionally, I teach AI courses at universities here in Korea. So I bring both practical industrial experience and a passion for simplifying complex concepts, which I hope will benefit you throughout this course. Let's begin by addressing a key question. Why is this certification important? Does it guarantee a job? Not necessarily. Will it raise your salary? Probably, but not a given. However, what it does offer is credibility. In a competitive field like machine learning, having a certification from AWS shows that you have the knowledge and skills to apply machine learning solutions within AWS's cloud environments. Think of it as a validation of your ability to work effectively in real world business scenarios where cloud based machine learning is increasingly important. So, what exactly does this certification validate? AWS describes it as proof that you can design, build, deploy, optimize, train, tune, and maintain machine learning solutions for business problems using the AWS cloud. This isn't just theoretical knowledge, it's about demonstrating your ability to implement scalable, cost efficient, and secure machine learning solutions on AWS. It shows you understand both the technical and operational aspects of building and managing ML systems. Now, who is this course designed for? Whether you are a student or a working professional, this course is perfect for those aiming to pass the AWS certified exam, machine learning exam. AWS recommends candidates to have at least 2 years of experience in developing or architecting machine learning workloads, especially in the AWS cloud environments. But don't worry, while this is a guideline, it's not a strict requirement. If you've got some fundamental knowledge of machine learning, this course will equip you with the specific knowledge and skills needed to pass the exam. So, why should you choose this course? I've designed it with a clear goal in mind to help you pass the AWS certified machine learning exam efficiently. There are many courses out there that aim to teach you everything about AWS, but let's be honest, trying to master every feature of AWS while preparing for a certification exam isn't realistic in a short time frame. This course is laser focused on what actually shows up in the exam by closely following the official AWS exam guide. We'll ensure that you concentrate on the most important topics without unnecessary detours. In short, we are studying smart, not hard. Here is a piece of practical advice. Should you spend months and months preparing for this certification, like you might for a CPA or CFA exam? In my view, no. The field of AI is moving too fast to invest all your time into just one certification. The goal here is to learn efficiently, pass the certification, and move on to staying current with the latest trend in machine learning, like generative AI models or the newest research papers. This course helps you prepare quickly so you can focus your time on what's next in your career. Now let's talk about how this course is structured. This course is composed of 72 concise lectures, each between 5 and 8 minutes long. These short and focused lessons will cover essential topics such as data engineering, exploratory data analysis, modeling, and machine learning implementations and operations, all aligned with the AWS exam guide. You'll focus heavily on real exam questions. I'll keep theoretical concepts to a minimum and provide the supplementary materials where needed. If you are completely new to machine learning, this course might feel challenging. But if you have some fundamental knowledge, you should find it manageable. And if you ever hit a rough patch, I'll guide you to the right resources to help you through it. In summary, this course may not be the most comprehensive exploration of AWS's machine learning capabilities, but it is designed to be the most efficient path to passing the certification. For those of you with limited time and a strong desire to get certified quickly, I believe this is the best option. I'm looking forward to taking this journey with you, and I'm confident that together we can achieve your certification goals. I'll see you in the next session. Now that we are moving into the second session, let's take a closer look at the structure of the AWS Certified Machine Learning Specialty exam and the different question types you'll encounter. The exam is divided into four major domains, each of which tests your ability to perform various machine learning related tasks within AWS. We'll go through each domain and its weight on the exam, offering insights into the skills you'll need to succeed. Let's start with data engineering, which makes up 20% of the exam. Now, some of you might wonder, why is data engineering such a significant part of a data science certification? Well, the reality is that data engineering plays a huge role in the day to day work of data scientists. You rarely spend all your time just modeling or researching. A lot of time, you're preparing and managing data, which makes this domain essential knowledge. Let's break down what you'll need to know. First up is create data repository for machine learning. This simply means understanding how to store your data in AWS. You'll need to know which types of storage services are available, like Amazon S3, Amazon Elastic File System, or Amazon Elastic Block Store, and how to decide which one to use depending on the type of data you're working with. Next, you'll need to identify and implement a data ingestion solution. In a simple term, this means figuring out how to bring the data into your system. This could be a batch load, a streaming job, or any other data pipeline. This is an area where junior data scientists or students often struggle because in non-business environment, you rarely need to worry about where the data comes from. But in the real world, especially in the cloud, you must understand how to orchestrate these ingestion pipelines using tools like Amazon Kinesis, AWS Glue, or Amazon EMR. Finally, identify and implement a data transformation solution. This involves understanding tools like ETL pipelines using AWS services like AWS Glue or EMR. The idea is to transform your data into a usable format for machine learning models, often using tools like Apache Spark or Hadoop for large scale data processing. Understanding data engineering will not only help you in the exam but also prepare you for real world scenarios where managing data efficiently is key. Next is exploratory data analysis, which covers 24% of the exam. Exploratory data analysis, or EDA, is all about getting to know your data before you dive into modeling. This domain focuses on how well you can clean, visualize, and extract meaningful information from the raw data. One of the core skills tested here is how to sanitize and prepare data for modeling. This includes identifying missing or cropped data and knowing how to handle it, whether that's through imputation, deletion, or other methods. You'll need to normalize, scale, and format your data correctly. Another key area is feature engineering. This is where you extract useful features from the data that will help improve your model's performance. You might be asked about techniques like one-hot encoding or dimensionality reduction. The idea is to transform raw data into features that can be fed into your model, which can sometimes involve a lot of trial and error. But it's also where you can be most creative. Finally, data visualization is tested as part of this domain. You need to be able to create visualization like sketch plots, histogram, and time series graph to better understand your data. These visualizations help identify patterns, trends, and outliers, which can dramatically impact your model's success. Exploratory data analysis is a critical part of the machine learning process. Getting this step right means you are setting up your models for success later on. Now we move on to modeling, which takes up the largest portion of the exam at 36%. At its core, this domain is about building machine learning models that solve real world problems. But it's not just about knowing how to code or use frameworks, it's about understanding when and how to apply machine learning to a given business problem. First, we'll need to know how to frame business problems as machine learning problems. This means understanding when to use machine learning and when a simpler solution might be more appropriate. We'll also need to distinguish between supervised and unsupervised learning and be able to select the appropriate model for the task, whether it's classification, regression, or clustering. Once you have identified the right model, the next step is training your model. The exam will test your knowledge of splitting your data into training and validation sets, choosing the right optimization techniques, and selecting the appropriate computing resources for training, whether it's CPU, GPU, or a distributed setup like Apache Spark. And don't forget hyperparameter optimization. This is the process of fine tuning your model to achieve the best performance using techniques like L1, L2 regularization, or cross validation. Finally, model evaluation is critical. You'll need to understand how to evaluate your model's performance using metrics like accuracy, precision, recall, and AUC/RC curves. This ensures your model is not just accurate but also avoids common pitfalls like overfitting and bias. In short, the modeling domain tests how well you can apply machine learning theory in a practical business context. All right, let's move on to domain 4, machine learning implementation and operation, which covers 20% of the exam. These domains focuses on everything need to take your machine learning model from deployment to fully operational states in production. Let's break it down. First, building machine learning solutions for performance and scalability. You need to ensure your models are well monitored and logged. AWS services like CloudWatch and CloudTrail are essential for tracking your environments. Deploy models across multiple AWS regions and availability zones to ensure scalability and fault tolerance. Using tools like auto-scaling, Docker containers, and AMIs, Amazon Machine Images for efficient, resilient deployment. Right sizing your resources helps optimize both cost and performance. And don't forget to implement a load balancing to handle varying loads. Second, selecting the appropriate machine learning services and features. For various use cases, you'll need to choose the right AWS machine learning services. For example, Amazon Poly, Alex, and Transcribe are useful for text and speech tasks. You should also understand service quotas. SageMaker built-in algorithm versus building your own custom models. Cost effectiveness is key. Consider using spot instances using AWS batch to training deep learning models efficiently. Third, applying AWS security best practices. Security is crucial in machine learning pipelines. This means setting up IAM roles, S3 bucket policies, security groups, VPCs, and data encryption to ensure your models and data are safe. Finally, deploying and operationalizing machine learning solutions. Once your model is ready, you need to expose endpoints for interaction. You should also understand how to perform A/B testing to evaluate model performance and set up retraining pipeline to keep your model updated. Debugging and troubleshooting are important skills, so you can detect and resolve any drops in performance while continuously monitoring your model's health. So that covers the four domains of the AWS Certified Machine Learning Specialty exam: data engineering, exploratory data analysis, modeling, and machine learning implementation and operations. Each domain challenges a different aspect of your skill set, from managing data to building and deploying models at scale. Remember, the key to passing this exam is understanding not just the theory behind machine learning, but how to apply using AWS services in real world scenarios. In the next session, we'll go into more detail about the specific types of questions you can expect in the real in the exam and how to tackle them effectively. Okay, welcome to lecture 3. Today we'll explore the types of questions you encounter on the AWS Certified Machine Learning Specialty exam. This lecture is all about understanding the format of the questions, which is crucial for approaching the exam confidently. There are two main question types you need to know. The first one is multiple choice. You select one correct answer out of four options. The incorrect options or distractors are designed to seem plausible, so careful elimination is key. The second one is multiple response. Here, you choose two or more correct answers from at least five options. To earn credit, you must select all correct answers. So here is a quick tip. Unanswered questions are marked as incorrect but there's no penalty for guessing. Always select an answer even if you're unsure. Now let's look at how your results are scored before diving into some sample questions. So let's quickly discuss the scoring system. The exam uses a scaled score between 100 and 1000 points. To pass, you need at least 750 points. The scoring model is compensatory, meaning you don't have to perform perfectly in every section. You just need to meet the overall passing score. Each domain carries a different weight, with modeling being the most significant at 36%. Your score report will also show your performance in each domain, helping you identify strengths and areas to improve. As you prepare, focus on the domains with the highest weights to maximize your score. Now let's analyze sample questions to understand the structure of these question types. So let's start with a multiple choice question. This type of question is the most common on the AWS Certified Machine Learning Specialty exam. Here's how it works. You'll be presented with four options and need to select one correct answer. The incorrect options, also called distractors, are designed to seem plausible by including similar concepts. This is why it's important to carefully analyze the question and eliminate the wrong answers systematically. Remember, there's no penalty for guessing. So even if you're unsure, make sure to select an answer. Now let's look at an example. A machine learning team has several large CSV datasets in Amazon S3. Historically, models built with the Amazon SageMaker linear learner algorithm have taken hours to train on similar sized datasets. The team's leaders need to accelerate the training process. What can a machine learning specialist do to address this concern? Option A, use Amazon SageMaker pipe mode. Option B, use Amazon Machine Learning to train the models. Option C, use Amazon Kinesis to stream the data to Amazon SageMaker. D, use AWS Glue to transform the CSV dataset to the JSON format. So take a moment to analyze the question. Notice the key phrase here. Accelerate the training process. This indicates the focus is on performance optimization. So the correct answer is A. Use Amazon SageMaker pipe mode. So for option A, SageMaker pipe mode streams data directly from S3 to the training container, which reduces startup times and optimizes throughput. This is the best solution for accelerating training. For the option B, Amazon Machine Learning is depreciated and not suitable for modern workloads. And for the option C, Kinesis is for real-time data ingestion, not for speeding up SageMaker training. And for option D, AWS Glue transforms data but does not affect training performance. So this example highlights the structure of multiple choice questions. For options with one clear answer. So pay attention to key terms in the question and eliminate the distractors logically. Now let's move on to a multiple response question. This type of question requires you to select two or more correct answers from at least five options. To get credit, you must select all the correct answers. These questions test your ability to recognize how AWS services work together to solve a problem. So here is an example. A company has an e-commerce website with a product recommendation engine built in TensorFlow. The recommendation engine endpoint is hosted by Amazon SageMaker. Three compute-optimized instances support the expected peak load of the website. Response times on the product recommendation page are increasing at the beginning of each month. Some users are encountering errors. The website receives the majority of its traffic between 8 a.m. and 6 p.m. on weekdays in a single time zone. Which of the following options are the most effective in solving these issues? Solving the issue while keeping costs to a minimum. So you have to choose two options. The first one is configure the endpoint and to use Amazon Elastic Inference Accelerator. Option B is creating a new endpoint configuration with two production variants. Option C is configure the endpoint to automatically scale with the invocations per instance metric. And option D is deploy a second instance pool to support a blue-green deployment of models. Option E is with configure the endpoint to use burstable instances. So actually the correct answer is B and C. So B is creating two production variants. It allows resource allocation during peak and off-peak traffic periods, which improves performance without significantly increasing costs. And for the option C, auto-scaling with the invocation per instance metric dynamically adjusts resources to match traffic demands, reducing costs during quiet periods. So this question highlights the complexity of multiple response questions. You'll need to carefully evaluate each option and consider which combination best addresses the scenario. So remember, you must select all correct answers to earn credit. So don't stop at just one. So in this lecture, we reviewed two primary question types on the AWS Certified Machine Learning Specialty exam. The first one is multiple choice, one correct answer out of four options. The second one is multiple response, two or more correct answers from at least five options. So we also analyze sample questions to understand how to approach and eliminate incorrect answers. Remember, these questions are designed to test your ability to apply AWS services to real-world scenarios. So pay close attention to keywords in the questions and don't hesitate to guess if you are unsure. In our next lecture, we'll dive deeper into the first domain, data engineering, and discuss how to identify and manage data sources. So thank you, and I'll see you in next time. Welcome to the data engineering domain. Today, we'll explore how data engineering supports machine learning workflows. Data engineering forms the foundation of machine learning projects. It ensures that raw data from various sources is stored securely and efficiently in the right repositories and collected and processed through a well-designed ingestion pipelines and transformed and prepared to be usable for model training. These tasks are essential for building reliable and scalable machine learning solution. So let's start with the first task, creating data repository. The first task in data engineering is creating data repositories. This starts with identifying your data sources. For example, user activity logs, IoT sensor outputs, or financial transactions. Each type of data requires a suitable storage solution. And AWS offers various options for this. Database like RDS and DynamoDB is ideal for structured and queryable data. And Amazon S3 is best for large scale unstructured data sets like images or log files. In Amazon EBS is perfect for high performance workloads that require scalable file storage. So selecting the right storage solution ensures your data is accessible, secure, and cost effective. Once your data is stored, the next step is building data ingestion pipelines to move it into your machine learning workflows. There are two primary styles of data ingestion. The first one is batching processing. Batching processing is for periodic updates, such as daily or hourly data loads. AWS Glue is a great tool for automating these tasks. And the second one is streaming processing. Streaming processing handles real-time data like click streams or IoT feeds. So AWS provides tools like Amazon Kinesis and manages service for Apache Flink for these scenarios. Additionally, Amazon EMR is a powerful option for processing larger scale datasets, especially when using Apache Spark or Hadoop. The key is selecting the right ingestion method based on your case. The third task in data engineering is transforming data to make it usable for machine learning. This step typically involves ETL, extract data, transforming transforming into a usable format, and loading it into a system for analysis. And AWS Glue is commonly used for this purpose, along with AWS Batch for large-scale transformations. So for machine learning specific data handling, MapReduce frameworks like Apache Spark and Hadoop are essential tools. They can efficiently process larger datasets while performing operations like cleaning, normalization, and feature extraction. By the end of this step, your data should be clean, structured, and ready for training. So why is data engineering so important for machine learning? First, it ensures that your data is high quality and readily accessible. Poorly prepared data can lead to inaccurate models and wasted resources. Second, robust data engineering supports reliable machine learning workflows by minimizing errors during training. And lastly, it optimizes storage and processing, reducing costs while improving scalability. This makes your machine learning project more efficient and effective. So in this lecture, we've introduced three core tasks of data engineering: creating data repositories, building ingestion pipelines, and transforming data for machine learning. In the upcoming lectures, we'll dive in deeper into each of these areas. We'll explore how to choose the right storage solutions, build efficient pipelines, and transform data for specific machine learning use case. Thank you for joining, and I look forward to seeing you in the next session. So, machine learning projects start with data. In identifying the right data source is the very first step. Without relevant, accessible, and high quality data, even the best machine learning can fail to deliver meaningful results. So, when evaluating data sources, you need to think about three key factors. First, is the data relevant to your machine learning objectives? For example, if your goal is to predict customer churn, you will need historical customer interaction data. Second, is the data easily accessible and in what format? Data stored in different formats or locations might require extra effort to integrate into your machine learning pipeline. And finally, is the data of good quality? This means it should be complete, accurate, and free from inconsistencies. Poor data quality often leads to unreliable models. In this lecture, we'll explore the types of data sources you might encounter and how to identify the most appropriate ones for your machine learning project. So there are three primary types of data sources to consider in your machine learning workflows. First, we have structured data, which is highly organized and stored in relational database or data warehouses. Examples include customer records or sales transactions. AWS offers powerful tools like Amazon RDS and Amazon Redshift for managing structured data. Next is unstructured data, such as images, videos, and logs. These data types don't fit neatly into rows and columns, but are often crucial for machine learning applications like image recognition or sentiment analysis. Amazon S3 is a go-to solution for storing large volume of unstructured data, and services like Amazon Recognition can help analyze it. And finally, there is training data too, which arrives in real time, such as IoT sensor data and click streams from a website. AWS tools like Amazon Kinesis and managed service for Apache Flink are designed to handle streaming data efficiently. Understanding these categories helps you match your data sources with the appropriate AWS services, ensuring a seamless and efficient workflow. When identifying data sources, it's important to consider pre-existing datasets that can save you significant time and efforts. AWS offers a rich repository of public datasets through its registry of open data on AWS. This registry includes datasets from various domains, such as weather data, um, and genomics, and satellite imagery. These datasets are pre-collected, publicly available, and ready to use in machine learning workflows. For instance, you might use satellite imagery for land use classification or genomics data for bioinformation research. When working with unlabeled data, you can leverage AWS tools to streamline labeling tasks. AWS SageMaker Ground Truth is a powerful service that uses machine learning to automate data labeling, reducing manual efforts. For more customized or manual tasks, you can use Amazon Mechanical Turk, a crowdsourcing platform, to label data at scale. For the real-time data collection, AWS provides Amazon Kinesis, which is designed to handle high throughput streaming data. Whether it's ID sensor readings or clickstream data from your website, Kinesis ensures you can ingest and process data in real time. Once you have identified your data sources, the next step is managing them efficiently. AWS provides several services to help you with this. For data discovery, AWS Glue Data Catalog is a powerful tool that allows you to organize and understand your data across multiple environments. To integrate your data into workflows, you can use services like AWS Data Pipeline or AWS Glue. These tools help you move and transform data seamlessly, preparing it for machine learning. AWS ensures the data is managed securely and scalably, enabling reliable machine learning workflows. By leveraging these tools, you can focus on building accurate models rather than worrying about data logistics. In this lecture, we have taken a deep dive into identifying data sources for machine learning. We have covered both public and private data sources, highlighted the value of AWS public datasets, and discussed the tools like Amazon's SageMaker, Ground Truth, and Mechanical Turk for efficient data labeling. Additionally, we explored real-time data ingestion with Amazon Kinesis. The next logical step in our data engineering journey is to discuss data storage mediums, starting with database. In the next lecture, we'll learn how to store structured data efficiently using services like Amazon RDS and DynamoDB. And thank you for your attention, and I look forward to seeing you in the next session. Welcome to today's lecture on data storage mediums in AWS. In this session, we'll cover three key storage services: Amazon S3, EBS, and EFS, and discuss how they fit into your data engineering and machine learning workflows. These storage services form the foundation for handling data in AWS, and understanding their strengths and use cases will help you make better decisions, and not just for the exam, but also in real world projects. Data storage is a critical component of any machine learning workflow. It determines how efficiently you can access and process data, how scalable your pipeline is, and even how much you spend. AWS provides several storage options, but today we'll focus on Amazon S3, EBS, and EFS. These services address different needs, such as object storage for scalability, block storage for performance, and file storage for shared access. By the end of this lecture, you will know exactly when and why to use each one. Let's start with a quick overview. AWS S3 is an object storage service designed for scalability and durability. It's perfect for storing unstructured data like logs, images, or backups. And Amazon EBS, on the other hand, is block storage. Think of it as high performance storage solution that work closely with EC2 instances, often used for database and transactional data. Finally, Amazon EFS is a file storage service. It allows multiple EC2 instances to access shared files, making it ideal for collaborative workflows or large scale analytics. Amazon S3 is a cornerstone of AWS storage services, designed for unlimited scalability and seamless integration with other AWS tools. One of S3's key strengths is its ability to serve as a data lake. You can store raw data sets, process the data, or even find results for long-term storage. So what's more, S3 integrates effortlessly with services like Amazon Athena, enabling you to run SQL queries directly on your data without moving it and as well. In machine learning workflows, S3 often serves as the starting points, whether for training data, backups, or analytic pipelines. Its versatility makes it an essential tool for data engineers and data scientists alike. And here is a breakdown of Amazon S3 storage classes and visualized in this chart. Each class is optimized for different access patterns and cost requirements, making it crucial to select the right one for your workload. Let's go through them briefly. First one is S3 standard. So ideal for frequently accessed data. It offers millisecond access and stores data across three available zones, aka AZ. Think of it as the go-to option for active datasets. And the second one is S3 intelligent tiering. It's perfect for workloads with unpredictable access patterns. It automatically moves data between frequent and infrequent tiers to save cost with minimal overhead. And the third one is S3. Oh, sorry. And the third one is S3 standard IA, infrequent access. It's designed for data that is accessed less frequently but still requires fast retrieval. It costs less per gigabyte but includes retrieval fees, so making it ideal for backup data. The first one is S3 one zone IA. It's similar to standard IA but stores data in a single AZ. It's less durable but more cost effective for non critical and recreatable data. The next one is S3 Glacier. It's built for archival storage, and data retrieval takes minutes or hours, but the cost per gigabyte is significantly low. So it's great for long-term backups. And the final one is S3 Glacier Deep Archive. It's the lowest cost option and designed for compliance and rarely accessed data. Retrieval times are longer, around 12 hours to 48 hours, but it's perfect for data you hardly ever need to touch. So, now for the exam, remember this: frequent access, go with standard or intelligent tiering. Infrequent access, choose standard IA or Glacier. Long-term archiving, Glacier Deep Archive is the way to go. So make sure you understand the trade-off between cost, access frequency, and durability when choosing the storage classes. And now let's talk about Amazon EBS. And EBS is all about performance and persistency. Persistence, and it provides block level storage, making it a great choice for applications that require high IOPS, like database or transaction heavy workloads. EBS comes in two primary steps. It comes in two primary types. The first one is a general purpose SSD, which balances cost and performance, and the other one is provisioned IOPS SSD, which is designed for mission critical workloads, which provisions with provisioned IOPS SSD, you can achieve up to 256,000 IOPS, ensuring low latency performance. So remember, EBS must be attached to an EC2 instance. This means it's ideal for workloads that need direct, low latency access to data. And with features like snapshots or backups and encryption handled automatically, EBS is reliable and secure. Now, now that we've covered Amazon EBS, let's move on to Amazon EFS, or Elastic File System. EFS is all about shared access and scalability, making it a unique solution compared to S3 and EBS. Let's take a look at some key use cases where EFS really shines. The first use case is big data analytics. In distributed processing environments like Apache Spark or Hadoop, multiple instances need to access the same datasets simultaneously. So EFS provides a shared file system that scales as your data grows and making it ideal for collaborative big data workloads. And next we have application development. For teams working on shared projects such as storing and managing code or media files, EFS serves as a central repository accessible by all team members. Whether it's code repositories or large datasets used for testing, EFS provides seamless access. Finally, content management system or CMS. These systems often require multiple users to share and update files in real time, such as managing digital assets for websites or collaborative content platform. EFS shared file storage capability makes it perfect for these environments. So in summary, if your workloads require shared scalable storage with low latency access across multiple EC2 instances, EFS is the go-to solution. Now we have explored each services, so let's compare them. The first one, S3, is your go-to for scalability and cost optimization. Think unstructured data like logs or images. And Amazon EBS is all about high performance for a single instance. If you're running a database or transactional workloads, this is your best choice. And Amazon EFS is designed for shared access and collaboration. It's perfect for machine learning training or a distributed system. When deciding which to use, start with your workload requirements. If you need scalability, go with S3. If you need performance, choose EBS. And if you need shared storage, EFS is your answer. Okay, welcome to part 2 of our lecture series, Mastering Real World Scenarios. In part 1, we explored the core concepts of Amazon S3, EBS, and EFS, examining their features, use cases, and how they fit into data engineering workflows. While it's essential to understand the theory, mastering the practical application of these services is equally important, especially for the AWS Certified Machine Learning Speciality exam. Our class is designed for fast-paced learning, and while it would be ideal to practice every possible scenario, we'll focus on the key points that are most likely to appear on the test. In this session, we'll analyze real-world scenarios based on actual exam questions and slight variations. And these problems will test your ability to identify the right storage solution for a given workload. So let's dive into our first question and start applying what we've learned. Okay, our first question is as follows. A data science team is designing a repository to store a large amount of training data commonly used in its machine learning models. The data scientists need a solution to scale automatically as new datasets are created daily and be cost effective for storing data. Support SQL queries for exploring the data. Option A, store datasets as file in Amazon S3 and store dataset. Option B is store dataset as files in an Amazon EBS volume, attach it to an EC2 instance. And C, store datasets as tables in a multi-node Amazon Redshift cluster. And option D, store datasets as global tables in Amazon DynamoDB. So take a moment to analyze the question. Notice the bolded phrases: scale automatically, cost effective, and support SQL queries. These are your key indicators for identifying the right AWS service. Now, based on these keywords, which option do you think is correct? Keep your answer in mind and let's move on to the explanation. The correct answer is A. Store datasets as file in Amazon S3. Why this is the best choice? So S3 provides scalability and cost efficiency. Additionally, it integrates seamlessly with Amazon Athena, allowing SQL queries to be run directly on data stored in S3. And EBS is not scalable for this use case. It's tied to single EC2 and does offer SQL query capabilities. Use EBS for lower latency, single instance storage like um, transactional databases. And Redshift is powerful data warehouse solution, but it's not cost effective for storing large raw data sets or training data. It's better suited for structured analytical workloads. And our fourth option, the DynamoDB is no SQL database, NoSQL database, and optimized for key value or document-based storage. It doesn't support raw file storage or SQL querying, making it unsuitable for this scenario. So here's tips for the exam. When you see terms like scale automatically, cost effective, and SQL queries, think of Amazon S3 and its integration with Athena. It's a versatile solution for storing large unstructured datasets. Now our second question is, a company is training machine learning models on Amazon SageMaker with 200 terabytes of data stored in Amazon S3. The files are over 200 megabytes in size. The company requires the shortest processing time and minimal setup for training. So here is the keyword, and let's look at the options. Option A, use file mode in SageMaker to copy the dataset from the S3 buckets to the machine learning instance storage. And option B, create an Amazon FS for lost tree file system and link it to the S3 buckets. And option C, create an Amazon Elastify system, EFS, and mount it to the training instances. And the last option is use fast file mode in SageMaker to stream the files on demand from the S3 buckets. So notice the bold terms here: shortest processing time and minimal setup for training. So these keywords are crucial in narrowing down the options. Keep this in mind and as we evaluate the correct answers. So the correct answer is D. Use fast file mode in SageMaker. So option A, file mode copies the data to the instance, which increases setup time significantly when dealing with a large dataset. But this doesn't meet the shortest processing time requirements. And B, FS is for lottery works. It works very well with S3, but adds complexity and cost compared to fast file mode. And option C, EFS is not optimized for SageMaker and would cause delays with large files. And these correct answers because a fast file mode allows SageMaker to stream data directly from S3, and without copying it to the local storage, which is so therefore it reduces the both setup and processing times. So here's tips for exam. If you use silly large datasets and minimal setups for a SageMaker, fast file mode is the best choice. Our third question focuses on shared access and high throughput workloads. Here is the scenario. An organization is processing real-time data streams from IoT sensors. The data needs to be temporarily stored and then processed by multiple EC2 instances running analytics. Quite familiar, right? The storage solution must be optimized for shared access and capable of handling high throughputs, parallel workloads. Let's see the option now. Let's check the option. Option A, Amazon S3 with transfer acceleration. B, Amazon Elastic File System. C, Amazon EBS with the provisions IOPS. Option D, Amazon FS for loss trade. So take a key phrase here, shared access, high throughputs, parallel workloads. This will guide you to the correct answer. Let's see what it is. The correct answer is B, EFS. So for S3 is not designed for temporary storage or real-time access. And EBS is not suitable for multi-instance access. And it is tied to single EC2 instances. And FS for S3 supports high performance workloads but is optimized for data lake and HPC, not temporary storage. So the correct answer is B. EFS supports high throughputs and shared access, making it ideal for real-time processing across multiple EC2 instances. So our final question addresses archiving and compliance. Here is the scenarios. A trucking company collects daily image data from its fleet, which generates 100 gigabytes of new data per day. The company wants a cost-effective solution for storing and archiving the images, versioning for compliance, and automatic replication of data to another AWS region. Option A is AWS S3 with S3 cross-region replication. Option B is EFS standard storage. Option C is EBS with snapshots replicated to another region. And option D is AWS storage gateway. So focus on the bolded keywords, archiving, and versioning, and cross-regional. Let me see, cross-regional replication. So these are the hints you need to find the right answer. The correct answer is A, Amazon S3 with S3 cross-region replication. S3 is cost-effective for large-scale storage, supports versioning for compliance, and enables CRR for automatic replication across regions. EFS doesn't support versioning, or cost-effective archiving. It's designed for shared file systems, not object storage for compliance. EBS snapshots provide replication, but are far more expensive than S3 for storing large data sets like images. So it's not cost effective at all. And for option D, AWS Storage Gateway is used for hybrid cloud storage, non-native AWS storage solution optimized for archiving or versioning. So it's not ideal for native AWS storage needs. So for keywords like versioning, archiving, or replication, S3 with CRR is the best choice here. So congratulations, we've just completed our practice sessions on real-world scenarios involving Amazon S3, EBS, and EFS. In this session, we solved 4 exam-style questions and explored why each correct answer works, as well as why the other options don't. Here is a quick recap of what we've learned. So Amazon S3 is best for scalable, cost-effective object storage with integration options like Athena and CRR. Amazon EBS is the go-to choice for high-performance, single-instance workloads requiring low latency. And Amazon EFS shines in shared file storage and high throughput parallel workloads. Keep these key concepts in mind as you prepare for the exam. Remember, recognizing keywords like scalability, shared access, or versioning will guide you to the right answer. So thank you for joining this session, and I'll see you in the next lecture. So welcome to today's lecture. We are diving into an important concept for machine learning workflows: data job styles and types. Broadly, there are two ways to process data: batch processing and streaming processing. So let's start with batch processing. Batch processing involves work with data in periodic chunk. Think of tasks like running a daily sales report or generating a weekly customer summary. It's not immediate. You process all the data at once, which can take anywhere from minutes to hours. An AWS service like AWS Glue, AWS Batch, and Amazon EMR are built for these types of jobs. On the other hand, streaming processing happens in real time. It's designed for data that arrives continuously, like IoT sensor readings or clickstream data from a website. Streaming jobs handle data as soon as it's generated, which makes them ideal for real-time monitoring or analytics. For these jobs, AWS tools like Amazon Kinesis manage the service for Apache Flink and AWS Lambda. These are the go-to solutions. So understanding the difference between these two styles is crucial for choosing the right AWS service for your workload. Now let's break this down further by comparing batch and streaming jobs side by side. So here is a clear comparison of batch processing and streaming processing. So first, look at the data arrival. Batch jobs work with data that arrives in periodic chunks. It's collected over time and processed later. Streaming, by contrast, works with data as it's generated in real time. The next one is the latency. Batch processing tends to have high latency because it waits to process all the data at once. This is fine for use cases like ETL jobs or monthly reports streaming. However, operates with low latency, often in the range of seconds or milliseconds, which is essential for real-time insights. Then think about the use cases. So batch processing is perfect for historical reporting or transforming data in bulk. Streaming shines when you are handling real-time monitoring or IoT workloads. And finally, AWS tools. Batch jobs rely on services like AWS Glue, EMR, and Batch. For streaming, you look at Kinesis, Flink, and Lambda. For the exam, pay close attention to scenarios that mention real-time requirements or periodic processing. These are key clues that point you to either batch or streaming solutions. So let's test our understanding with practical question. A company runs daily sales reports using data from its Amazon S3 data lake. The reports must be ready by 8 a.m. each day. Which AWS service is best suited to schedule and orchestrate this job? Take a moment to think about the key phrase here, daily sales report. This immediately tells us we are dealing with batch processing. So the correct answer is A, AWS Glue. AWS Glue is an ETL service designed for batch processing. It integrates well with S3 and allowing you to schedule and orchestrate data jobs effortlessly. And the other options don't fit because Kinesis and Flink are built for real-time streaming, while DynamoDB is a database service, not the orchestration tool. For the exam, anytime you see a mention of scheduled processing or ETL workflows, think of AWS Glue, AWS Batch, or Amazon EMR. And now let's look at a streaming example. The company processes click streaming data from its website to monitor user behavior in near real time. The system must ingest data continuously and analyze data in real time. Which AWS service should the company use? There's two options here. So key phrases here are ingest data continuously and analyze data in real time. These are clear indicators of streaming processing. The correct answer are A and D. So here's why. Kinesis data stream handles the real-time ingestion of clickstream data, and Flink processes and analyzes the streams in near real time, offering insights almost instantly. And the other options don't fit because AWS Batch and Glue are batch processing tools, as we mentioned, and not designed for real-time workflows. For the exam, look for keywords like real-time and continuous data or low latency to identify streaming scenarios. And remember, Kinesis is for ingestion, while Flink is for processing and analytics. So in this lecture, we explore two main data job styles, batch processing and streaming processing. Batch jobs work with data in chunks and are great for historical reporting or ETL workflows. On the other hand, streaming jobs handle real-time data, making them perfect for monitoring or IoT workloads. And AWS offers a variety of tools for both styles. And understanding which to use in different scenarios is a critical part of the exam. Remember, pay attention to keywords like daily or scheduled or real-time low latency or continuous data to determine whether a batch or streaming approach is needed. And thank you for joining this session, and I'll see you in the next lecture where we'll dive deeper into data ingestion pipelines and how to orchestrate them effectively. Welcome to today's lecture on orchestrating data ingestion pipelines. In any machine learning project, your first step is always data, but it's not enough to just have data. You need a system to collect, organize, and prepare that data reliably. That's where data ingestion pipeline come in. In this lecture, we'll define what the data ingestion pipeline is and why orchestration is essential, and introduce the key AWS tools for building and managing these pipelines. This lecture will give you a solid foundation for upcoming sessions, where we'll take a deep dive into tools like AWS Kinesis, AWS Glue, Firehose, and more. Let's begin. First, let's define data ingestion. Data ingestion is the process of collecting data from various sources. This could include database, IoT devices, or logs, and preparing it for storage or analysis. For example, you might collect real-time sensor readings from IoT devices, or you might gather historical sales data from a rational database for batch processing. The purpose of the data ingestion is to ensure that data flows efficiently and reliably into your data storage or processing system. It's important to remember this is very first step in your machine learning workflow. Without a reliable ingestion pipeline, even the best models won't perform effectively because they will lack high quality and accessible data. Now, why do we need orchestration for data ingestion pipelines? Orchestration refers to the process of automating and managing the different steps in your pipeline. This becomes especially important when your data workflows involve multiple tools or complex dependencies. For example, if one step in your pipeline fails, orchestration can automatically trigger retries or recovery actions. Or if your incoming data volume spikes, orchestration can scale your resources dynamically to keep the pipeline running smoothly. Let's think about the real world scenario. Imagine you're collecting data from thousands of IoT devices in real time without orchestration. Handling errors, scaling, and maintaining efficiency would require significant manual efforts. And orchestration ensures that your pipeline runs reliably, efficiently, and can scale as your data grows. And now let's look at the AWS tools you can use to orchestrate data ingestion pipelines. The first one is Amazon Kinesis. This service is designed for real-time data ingestion. You can use it to collect and process streaming data from IoT devices, application logs, or website clickstream. The second one is Kinesis Data Firehose. Think of Firehose as a continuous delivery service. It takes streaming data from and sends it directly to destinations like S3 or Redshift or Elasticsearch. And next one is Glue. And Glue is a perfect solution for batch workflows, automating ETL tasks like cleaning and transforming data before loading it into your data lakes or warehouse. And EMR. This service is built for big data processing. It allows you to run frameworks like Spark or Hadoop for large scale analytics. And Apache Flink. Flink is designed for real time streaming processing. It's especially powerful when you need advanced analytics on data as it's ingested. Each of these tools plays a specific role in data ingestion pipelines. In upcoming lectures, we'll dive deeper into how and when to use each one effectively. Now let's wrap up with a quick summary. Data ingestion is the process of collecting and preparing data for your machine learning workflows. Orchestration ensures that pipelines are reliable, scalable, and automated. AWS tools provide robust solutions for managing these pipelines. Use Kinesis and Firehose for streaming data, and use Glue for batch ETL workflows, and use EMR and Flink for big data and real-time processing. In the next lectures, we'll take a closer look at each of these tools, starting with Amazon Kinesis. And thank you, and I'll look forward to seeing you in the next session. Welcome back. In this lecture, we'll explore data ingestion with Amazon Kinesis, one of the most powerful AWS services for real-time data streaming. Data ingestion is the starting point for any machine learning workflow, and Kinesis provides the tools to handle streaming data efficiently. Today, we'll break down the components of Kinesis, understand their use cases, and finish with some practice questions to solidify your understanding. Let's dive right in. So let's start with an overview of Amazon Kinesis. Kinesis is AWS's real-time streaming service designed to collect, process, and analyze streaming data. It's an essential tool for handling data in motion, such as IoT sensor readings, application logs, and click streams. Kinesis has three main components: data stream, Firehose, and data analytics. Data stream is for high throughput real-time data ingestion, while Firehose hosts for delivering data to storage or analytics services like S3 or Redshift. Data analytics for analyzing and transforming streaming data in real time using SQL or Apache Flink. There is also Kinesis Video Stream, which is designed for streaming and analyzing video data from sources like IoT cameras. However, video stream is out of the scope of this exam, so you just need to know that it exists. For now, we'll focus on three main components: data stream, fire host, and data analytics, which are directly relevant to your certification. Let's talk about key features of Kinesis and how they are used in real-world scenarios. Data stream. Data stream is the backbone of Kinesis, providing scalable and durable streams for real-time data ingestion. You can adjust throughput and partition your data using shards. It's perfect for applications like logs and event collection, real-time analytics, and gaming data feeds. And Firehose. Firehose is for delivering data directly to AWS destinations like S3 or Redshift, Elasticsearch. It even supports simple data transformation using AWS Lambda, making it ideal for IoT analytics, clickstream data, and log monitoring. The last one is data analytics. This component lets you analyze and transform streaming data in real time using SQL or Apache Flink. It's designed for advanced use cases like real-time ETL, stateful event processing, and security monitoring. Together, these tools cover a wide range of use cases, from IoT data sensor to fraud detection to real-time user behavior monitoring. Now, before we move to the question, let me briefly mention another Kinesis service, Kinesis Video Stream. Although it's not focus of this lecture, Kinesis Video Streaming is designed for real-time video streaming. If you're dealing with smart cameras or video-related machine learning, this is the service to explore. But for the purpose of our exam preparation, let's stick to the core components of data streams, Firehose, and data analytics. So let's test our understanding with practice question. A company is building a pipeline to ingest streaming data for real-time analytics. The data need to be transformed and stored in S3. What is the most cost efficient solution? Um, A. Use Amazon Kinesis data streams. B. Amazon Kinesis data firehose. C. Use AWS Glue. D. Use AWS EMR. So take a moment to think about the correct answers here. The correct answer is B. Use Amazon Kinesis data firehose to transform the data with an AWS Lambda function and deliver it to S3. So here's why. Firehose is built for continuous delivery and supports inline transformation with Lambda. It's cost effective and because it automates the entire process and integrates seamlessly with S3. The other options don't fit well as well because while um, data streams with Lambda can work, but it's more complex and less cost efficient. And for the option C, Glue is for batch workflows, not real-time ingestion. And EMR is too complex for this use case and adds unnecessary overheads. So key takes away from for the exam is that um, use Firehose when you need a simple transformation and real-time delivery to AWS storage or analytics services. So focus on some keywords like S3, simple transformations. And remember that data stream is for custom real-time processing and Glue is for batch jobs. Now let's look at another example. A financial company needs to process streaming transactional data in near real time for fraud detection. The solution must aggregate data over a 10 minutes window, deliver result to Amazon S3 for reporting. What is the best approach? So option A is data stream, option B is data analytics, option C is data Kinesis firehose, option D is Glue and EMR. So think about the requirements: real-time processing and window aggregation. Which service is purpose-built for this? The correct answer is B. Use Amazon Kinesis data analytics for apps Flink to aggregate data and write result to S3. So here is why. Kinesis data analytics supports windowed aggregation and real-time analytics. Apache Flink is specially designed for this type of processing. For the option A, Lambda doesn't natively support advanced windowing. And for C, Firehose can handle simple transformation but lacks advanced analytics capabilities. And for D, Glue and EMR are batch oriented, not real time tools. So use data analytics with Apache Flink for advanced real time analytics, especially when windowed operations are required. So to summarize, Kinesis is your go-to service for real-time data ingestion and processing. And data streams handles high throughput ingestion, while Firehose delivers data with simple transformations. And data analytics is for advanced real-time analysis using SQL or Flink. Remember to carefully evaluate the requirements in each scenario. Is it real time or batch? Does it need transformation or advanced analytics? By matching the right tool to the use case, we'll ace any question on Kinesis. Thank you, and I'll see you in the next lecture. So, welcome back. In this lecture, we'll dive into AWS Glue, one of the most essential tools for ETL workflows on AWS. First, what is Glue? AWS Glue is the serverless ETL service that makes it easy to extract, transform, and load data across multiple sources. is highly integrated with AWS services like S3, Athena, and Redshift, making it a go-to choice for preparing data for machine learning workflows. Now, why Glue? It offers three standout features. First one is Glue crawlers, which automatically discovers schemas and updates your data catalog. And the second one is Glue job, which allows you to write and automate complex data transformation. And the third one is serverless architecture, which means you don't have to manage the infrastructure. It scales automatically with your workloads. And for the exam, remember that Glue is built for batch ETL workflows, not real-time ingestion. Let's explore some common use cases to see where Glue fits best. So let's talk about how Glue is used in real-world scenarios. Data cataloging. Imagine you have a S3 buckets with thousands of files. Using Glue crawlers, you can automate schema discovery and create a catalog that tools like Athena can query directly. And data transformation. Glue jobs are perfect for format conversions like CSV to Parquet or for performing joins, aggregations, and mappings. This is essential when preparing datasets for analysis or machine learning. And third one is integration with machine learning pipelines. Glue seamlessly integrates with services like SageMaker to clean and pre-processing training datasets, making it a key part of any machine learning workflow. For the exam, pay close attention to scenarios that mention schema discovery, data transformation, or S3 integration. These are Glue's sweet spots. Let's test your understanding with a practice question. A company has 20 terabyte of data in a CSV format in an S3 buckets. They need to convert it to Apache Parquet format with minimal efforts. Option A. Use Glue crawler to convert the file. Or use option B. Write the script to convert the file format and run it as a Glue job. C. Write a script and run it on a EMR cluster. D. Use SageMaker for the ETL process. So take a moment to think about the correct answer. The key phrase here is convert the file format with the minimal efforts. What's the best AWS service for this task? The correct answer is B. Write the script to convert the file format and run it as a Glue job. So here's why. Glue jobs are specifically designed for automating data transformations like format conversion. It's serverless, cost efficient, and integrates natively with S3. Now look at other options. A is incorrect because Glue crawlers only discover and data catalog schema. They don't transform data. And C is incorrect because EMR requires more operational overhead and is not as simple to use as Glue. And D is incorrect because SageMaker is for machine learning tasks, not ETL workflows. So exam tips. When you see a question about format conversion or batch ETL, think of Glue job. And remember, Glue crawlers are for schema discovery, not transformation. And here is another question to test your knowledge. A data scientist is tasked with merging data from AWS Data Exchange with an Athena table. The transformation must complete in under 60 minutes, which is the most cost-effective solution. Option A, use Glue jobs with Lambda for transformation and merge the dataset. Option B, provision Redshift and perform transformation there. Option C, trigger Glue jobs via S3 events to merge data with Athena. Option D, use Lambda and SageMaker for the transformation. So the correct answer is C, trigger Glue job via S3 events to merge data with Athena. Here is why. Glue integrates seamlessly with Athena and can be triggered automatically by S3 events, making it cost-effective and fast for this case. And let's break down other options. A is incorrect because combining Glue and Lambda increases costs unnecessarily. And B is incorrect because Redshift is overkill for this scenario and more expensive. Option D is incorrect because SageMaker is not optimized for ETL workflows. So when you see keywords like Athena and R3 events, think of Glue jobs as your go-to solution. Glue is ideal for batch transformation that integrates with Athena. So to wrap up, here are the key points to remember about AWS Glue. Glue simplifies ETL workflows with its serverless architecture. Then Glue crawlers automate schema, discovery, and catalog updates. And Glue jobs are perfect for large-scale transformation like format conversions or data preprocessing. And Glue integrates seamlessly with S3, Athena, and Redshift, making it a cornerstone for machine learning pipelines. For the exam, focus on the differences between glue jobs and crawlers and remember when to use Glue versus other services like EMR or SageMaker. Thank you, and I'll see you in the next lecture. So, welcome back, everyone. Today, we are diving into AWS EMR, a core AWS service for big data processing. If you are dealing with massive datasets, think terabytes or even petabytes, and need to pre-process or analyze them efficiently, Amazon EMR is the service to use. It's built for scalability and works seamlessly with other AWS tools, making it a powerful solution for batch processing and data transformation. Let's explore what makes EMR so effective and how you can leverage it for your workflows. So, what exactly is Amazon EMR? EMR stands for Elastic MapReduce, and is AWS's fully managed service for big data pre-processing. It supports popular frameworks like Apache Spark, Hadoop, Hive, and Presto, which allows you to handle complex data if transformation, large scale analytics, and more. EMR is particularly useful for processing data stored in AWS services like S3, Redshift, or DynamoDB. The best part is designed to scale dynamically based on your workload. So whether you are working with a few gigabytes or petabytes of data, EMR adjusts to meet your needs. Think of EMR as the backbone for big data workflows, from ETL to advanced analytics. Now let's talk about why Amazon EMR is such a versatile tool. I'll start with its key features and then move on to real use cases. First, the features: scalability. EMR allows you to dynamically add or remove nodes as your workload changes. This means you can handle data spikes or reduce costs during downtime. And flexibility. It supports multiple frameworks like Spark, Hadoop, Hive, and Presto. This gives you the freedom to choose the best tool for your specific workloads. And integration. EMR works seamlessly with AWS services like S3 for storage and Redshift for analytics and DynamoDB for operational data. And cost efficiency. You can significantly reduce costs by using spot instances for non-critical nodes while keeping essential ones on demand. Now, how is EMR used in the real world? Let me give you a few examples. Large-scale ETL jobs. Imagine you have 500 terabytes of raw data in S3. You need to filter, aggregate, and transform it before loading it into Redshift for analytics. EMR is built for handling this kind of large-scale ETL work. And machine learning data preparation. Using Spark machine learning library and EMR can pre-process and transform datasets for machine learning pipelines, ensuring they are ready for training. And ad hoc queries. With tools like Hive and Presto, you can run interactive queries on massive datasets directly from your data lakes. And batch processing. Whether it's whether it's IoT sensor data or application logs stored in S3, EMR can process these workloads efficiently. So for the exam, focus on scenarios where large-scale processing, integration with S3, or frameworks like Spark are involved. EMR often shines in these cases. Let's test your understanding with a simple question. A company has 500 terabytes of data stored in Amazon S3. They need to pre-process the data by filtering and aggregating it before loading it into Redshift for analytics. Which AWS service is best suited for this case? So take a moment to think about it. The key phrase here is 500 terabytes of data, which signals a need for large scale processing. And what do you think is the best answer? So the correct answer is B, Amazon EMR. And EMR is designed for large scale batch processing and works seamlessly with S3 for data pre-processing. If your task involves filtering and aggregating massive data sets, EMR is the ideal choice. Here's another practical question. A company used Amazon EMR to run nightly Spark jobs for their data pipeline. The team wants to reduce the cost of their cluster without affecting job performance. Which approach should they take? A. Switch all nodes to spot instances. B. Use spot instances for core and task nodes while keeping the master node on demand. C. Use smaller EC2 instance types for all nodes. D. Migrate the workload to AWS Glue. The correct answer is B. Use spot instances for core and task nodes while keeping the master nodes on demand. Spot instances are cost effective for non critical nodes, but the master node must always remain on demand to ensure cluster reliability. Let's review the another options. A. Switch all nodes to spot instances can risk interruptions and compromising the cluster's stability. And using small instances may save cost but could reduce performance significantly. And for D, while Glue is a great service, it's not designed for the scale and flexibility required for nightly Spark jobs. So exam tip is here. When cost optimization is mentioned, remember this. Use spot instances for core and task nodes, but always keep the master nodes on demand for stability. To summarize, Amazon EMR is your go-to service for large-scale data processing with tools like Spark, Hadoop, and Hive. And it works seamlessly with S3, Redshift, and DynamoDB, making it the excellent choice for big data workflows. To save costs, use spot instances for non-critical nodes, but keep the master node on demand. For smaller scale ETL or serverless solutions, consider AWS Glue instead. Mastering YAML will prepare you for a range of exam scenarios, especially those involving big data processing and cost optimization. Thank you, and I'll see you in the next lecture. Welcome back, everyone. Today we are diving into the world of real-time data processing with AWS Managed Service for Apache Flink. Flink is a powerful open source framework designed for distributed stream and batch data processing. Amazon has integrated it into its ecosystem, providing a fully managed solution for real-time analytics. Real-time data processing is crucial in machine learning, especially for use cases like fraud detection, personalized recommendations, and IoT monitoring. Apache Flink makes it easier to analyze streaming data as it flows in, enabling us to derive insights and take action almost instantly. Let's start by understanding the key capabilities of Flink and its integration with AWS services. So, what exactly AWS managed service for Apache Flink? It's fully managed service that runs Apache Flink, a framework specifically designed for real-time stream and batch data processing. Here is why it's so effective. First, stateful processing. Flink retains state across events, which is critical for use cases like fraud detection or aggregating data over time. Second, fault tolerance. With built-in checkpointing and recovery, your applications can handle failures seamlessly without data loss. And the third one is integration. It integrates a fault list with AWS services like Kinesis and S3, enabling end-to-end data pipelines. These features ensure that your real-time applications are reliable, scalable, and easy to deploy. Now let's talk about why AWS Managed Service for Apache Flink is so valuable and the use cases is perfect for. Why use it? It's designed for low latency, high throughput workloads, ensuring your data pipelines stay responsive. And it's perfect for event-driven architecture, like systems that react in real time to user behavior or sensor data. Here are some key use cases. Real-time analytics. For example, analyzing clickstream data to understand user behavior on a website. Second, fraud detection. Flink can detect anomalies in transaction streams as they happen. And also, it aggregates and processes sensor events in real time, enabling predictive maintenance or environmental monitoring. The fourth one is event driven applications. Complex event processing pipelines are easier to build with Flink. So, our first question involves a financial institution using Apache Flink for fraud detection. Let's take a look at the problem. A financial institution uses Apache Flink to process streaming transactional data for fraud detection. The system must maintain state across events and recover from failures seamlessly, which AWS service feature makes this possible. So take a moment to review the options. A. Manage the service for Apache Flink's fault-tolerant state management. B. Kinesis data streams with enhanced fan-out. C. Amazon S3 for batch storage of processed events. D. Amazon EMR with Hive for real-time querying. Think carefully about the requirements, maintaining states, and recovering from failures. Let's reveal the answer. So the correct answer is A. It is correct because Flink's fault-tolerant state management allows it to handle stateful workloads, ensuring data consistency and recovery from failures seamlessly. This is critical for use cases like fraud detection. Just remember the key words here: stateful processing and fault tolerance. So here is our next scenario, which focuses on Apache Flink's ability to process time-based aggregation. A company processes IoT sensor data using AWS Managed Service for Apache Flink. The data needs to be aggregated over a 5-minute window before being written to S3 for a long-term storage. Which feature of Apache Flink makes this possible? The options are A. Kinesis data streams with aggregation. B. Flink's windowed aggregation feature. C. AWS Glue for batch transformations. D. Lambda with S3 events for aggregation. Take a moment to think about the process, streaming, aggregation, and time windows. Let's reveal the solution. The correct answer is B. Flink's windowed aggregation feature. B is correct because Flink's windowed aggregation enables time-based grouping of events, like aggregating IoT data over a 5 minutes window before writing to S3. A is incorrect because Kinesis doesn't support complex windowing logic natively. C is incorrect because Glue is for batch processing, not real-time streaming. D is incorrect because Lambda lacks the advanced aggregation capabilities of Flink. So please remember the keywords: windowed aggregations and integration with S3. So exam questions often test your ability to identify tools that align with the specific requirements, like time-based processing. Keep these key features in mind as you prepare. So now let's summarize what we've learned. So Flink on AWS is a robust tool for real-time data processing, enabling low latency and stateful transformation. And key integrations include Kinesis data stream, S3, and other AWS services for seamless data pipelines. And when preparing for the exam, focus on scenarios where Flink provides a clear advantage, such as running window aggregations or complex transformation. In the next lecture, we'll explore handling machine learning specific data with MapReduce. Okay, welcome back everyone. Today we are discussing 4 essential tools for handling machine learning specific data: MapReduce, Hadoop, Spark, and Hive. These tools are central to distributed data processing and are often used in machine learning workflows for tasks like feature engineering, data aggregation, and more. By the end of this lecture, you'll understand the purpose of each tool, how they fit into broader Hadoop ecosystem, and when to use them in machine learning specific scenarios. Let's get started. Let's begin by looking at Hadoop ecosystem. This diagram provides a high-level view of the tools and frameworks that make up the ecosystem. At the core, we have HDFS, or the Hadoop Distributed File System, which is responsible for storing data across multiple nodes. Next to it, we have MapReduce, the fundamental engine for processing data in a distributed manner. Above MapReduce, we see tools like Hive, Spark. Hive provides a SQL-like interface for querying data stored in Hadoop, making it easier for analysts and engineers to interact with distributed data. On the other hand, Spark. Spark is a modern engine that builds on MapReduce but adds real-time processing and advanced analytics capabilities. Lastly, the ecosystem includes additional tools like HBase for non HBase and HBase is for no non-SQL data, and Pig. Pig is for scripting data transformation, and OZ is for workflow orchestration. However, for today's lecture, we'll focus on MapReduce, Hadoop, Spark, and Hive, as they are most relevant to machine learning workflows. Now that we've seen where these tools fit into the ecosystem, let's break down their roles and compare them. MapReduce is the core programming model for distributed batch processing. It splits tasks into smaller parts, processes them in parallel, and combines the result. It's powerful but requires detailed coding and is better suited for straightforward batch tasks. And Hadoop acts as a platform. It combines HDFS for distributed storage and MapReduce for processing, making it a comprehensive solution for handling large datasets. And Spark is the modern engine. It builds on MapReduce but focuses on speed and flexibility, especially for machine learning workflows. Its in-memory processing makes it much faster than Hadoop for iterative tasks like feature engineering. Hive serves as the interface, allowing you to query distributed data using SQL-like commands. It's great for analysts who prefer SQL over programming. For the exam, remember these categories. MapReduce is the core, Hadoop is the platform, and Spark is modern and fast. Finally, Hive is SQL friendly. Now let's focus on how these tools are applied to machine learning workflows. MapReduce is excellent for batch tasks like filter logs, aggregating metrics, or joining datasets. Think of it as the go-to solution for straightforward, large-scale processing. And Hadoop is great for storing and processing massive datasets, particularly when you need distributed storage with HDFS. It's the backbone of many batch pipelines. And Spark shines in feature engineering and real-time processing. With its ML library, it's ideal for scaling transformations and handling streaming data. And Hive is perfect for querying and summarizing data. If you need descriptive statistics or to extract features using SQL, Hive is a great choice. The key takeaway is to match the tool to the task. For iterative machine learning workflows, Spark is often your best choice. For SQL-based queries or batch processing, consider MapReduce, Hadoop, or Hive. Let's put this into practice with a sample question. 다시 하겠습니다. Let's put this into practice with a sample question. A data scientist is processing transaction logs stored in S3. The workflow includes filtering data, aggregating totals, and calculating derivative metrics. Which combination of tools is most appropriate for processing and preparing these features for machine learning? The options are A. EMR with Hive QL queries. Option B is EMR with Spark ML library. C. EMR with the MapReduce workflows. D. Glue for real-time transformation. Take a moment to think about the correct answer. Take a moment to think about the correct answer. The key phrases here are derived metrics and features for machine learning, which suggests a tool that's optimized for machine learning workflows. So let's break it down. The correct answer is B, Amazon EMR with Spark Machine Learning Library. Spark Machine Learning Library is specifically optimized for machine learning workflows, providing tools for feature engineering and data transformations. So exam tip is here using when the question involves machine learning or iterative data transformation, Spark is most almost always the right answer. If a SQL based querying is a focus, um, think Hive. For large scale structured batch tasks, consider MapReduce or Hadoop. So let's wrap up with the key points. MapReduce is the foundation model for distributed batch processing. It's reliable for filtering and aggregating large datasets. And Hadoop combines distributed storage and processing into a single platform, making it ideal for batch workflow. And Spark is the modern, fast engine designed for machine learning workflows, particularly feature engineering and real-time processing. And Hive provides a SQL-like interface, simplifying querying and summarizing of big data. For the exam, remember these strengths: Spark for machine learning pipelines and real-time workflows, and Hive for SQL-based query, MapReduce and Hadoop for batch processing and storage. Understanding these tools and their roles in the Hadoop ecosystem will prepare you the variety of exam scenarios. Thank you, and I'll see you in the next lecture.